Hey you guys, this is notes number 4. Um, we are going to explore the tools to test for convergence for a power series, okay? So, right now, while you're taking notes, make sure that you guys have. Oh, what am I doing? Make sure that you guys have this document right here as well, okay? I sent you guys a Dropbox link through Remind. You just got to scroll back if you haven't downloaded it yet. I encourage you guys to print it out. It's easier to have it out in front of you, okay? So everything is not going to get covered today. We're only going to take it piece by piece, so don't worry. If you have questions, make sure that you ask, okay? Okay, so few things. What are we doing, right? And why are we testing for convergence? So remember how we were coming up with polynomial lookalikes, right? We were coming up with ways to represent non-polynomial functions using using polynomials. So for example, we had that sine function, right? And we found out that we could use pretty much all the odd degree terms. And make sure that you guys are practicing knowing the Taylor series expansion as well as the summation form. Here, the summation form was pretty much just when n starts at 0 and it goes all the way to an infinite amount of terms, and you're taking the summation of your general term. So pretty much this is a very shorthanded way of writing this expansion, okay? So for instance, if n was equal to 0, what you would get here is you would get negative 1 to the 0 power, x to the 2 times 0 plus 1 all over 2 times 0 plus 1 quantity factorial. That simplifies out to just x, which is exactly our first term there, okay? Now, if you did n equals 1, you would do the same thing, and then you would actually end up getting your second term, and so on, right? So this was just a fast way of spitting out all your terms without actually having to write out all of your terms. So at the end of that worksheet, we briefly discussed interval of convergence, right? Which is pretty much where they overlap, right? It's only helpful when we can come up with a polynomial lookalike, because if we can't, then really what's the point of it if we can't overlap it, right? If we can't mimic it. So what we're doing today is we're going to study the power series, which is pretty much the series without the variables, okay? So for instance, like 1 over 1 plus 1 over 2 plus 1 over 3, and it goes all the way on, all the way to forever, right? And 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. So we did this briefly at the beginning of I forget which notes. But if you were to calculate this, if you were to add 1 over 1 plus 1 over 2 plus 1 over 3 on your calculator, and you could go as far as you can, this right here would actually go to infinity, all right? That right there diverges, because the amount of area just gets infinite, right? When something diverges, it really doesn't help us out because there's no overlap, right? It doesn't get to a finite number. But you'll notice that certain series, like this one down here, the second one, actually comes out to some finite number. I can't seem to remember what it was. I think it was like 1.6 something. But the fact that it comes out finite tells us that this will converge. Okay? So converge meaning that it'll overlap, but also that the area will be finite, okay? It's only helpful when we can play with series that converge, because any series that diverges just goes to infinity, and there's no interest in that, right? Because What's the whole point of having a series that diverges? Because it doesn't give us any information, right? So you're learning all of these tests right over here throughout the next few lessons, right? To kind of test to see whether a series will converge or diverge, right? Okay, so it all sounds weird at first. So here's your first one, okay? This is called the nth term test for divergence. A lot of people just call it the divergence test. Both phrases are accepted, okay? I think divergence test is a lot simpler, but it's up to you. It's the nth term test for divergence. So a few things. You want to know how to use it and when to use it, okay? So you could think of this test as like your first filter, okay? So what you're doing is you're draining out, so you're pouring this through like a colander, if you will, okay? You're draining out all the bad series, all the series that diverges. Because remember, any series that diverges gives us no information. So we want to get rid of all the bad ones, okay? So this is always your first filter, meaning you always look for the divergence test first. Before you learn all these other tests over here, your very first go-to is, will it diverge, right? Okay, so take a look over here on that first line, all right? Now, you have to read this very carefully. The series will diverge if the limit does not come out to 0. So if it comes out to anything except 0, you can say that it will diverge. Okay, one more time. The series will diverge only if the limit does not come out to 0. If it comes out to anything else, it will diverge. Okay? But if you take a look at the converge part, there's a not applicable. Okay. So here's what you guys have to understand. If the limit actually does come out to 0, that doesn't mean the opposite statement. Okay? If the limit comes out to 0, that does not mean that it will converge. It just means that we don't have enough information yet. So we say that it's inconclusive. Okay? So in general, when you use this test, this is always your first filter. So you always run this test, okay? Whether it's on paper or mentally. And I'll show you guys how to use this. So here we go. We'll do a few. Here's example 1. And you can tell that this is a, let me get rid of that real quick. You can tell that this is a power series because there's no x variable. Okay, so we're testing very specific ones here, okay? Okay, so just write down part A right here, and then we'll start. So we look at this summation here, this power series, and what we're going to do is we're going to run our very first filter. So we are going to take the limit of our general term, 2 to the n, as n goes to infinity. Always, always. Okay? So what happens if n goes all the way to infinity here? Well, we have 2 to the n. There's no fraction here, so 2 to the n is just going to get larger and larger and larger and larger. So this here tells me that the limit does not exist. Okay? But more importantly, okay, does not exist. Is that not 0? Definitely, right? Which is definitely not 0. So according to our test, since the limit did not come out to 0, therefore, the series diverges. If you guys heard that, Siri just activated. I remember that happening a few times I think at least once every year. Anyways, the series diverges. Let me write this here. Now, every time you state whether a series will diverge or converge, you have to state how. Like, how did you know? What test did you run? So by the divergence test or the nth term test, it's up to you. And there you go. Okay, you'll get a better handle on this once we do a couple more, but that's basically it. So we run a test and then we make a conclusion. All right, here's part B. Write it down. Play when you're ready. So here we're going to run that divergence test. So we'll take the limit of that general term, n minus 1 over n plus 1, as n goes to infinity. Okay, now this is kind of what we rehearsed. N is getting really large, right? So let's recap real quick. If we were to talk about speed, the fastest moving function, okay, the fastest, can you guys remember what the fastest moving function is, or the fastest increasing function? Press play when you're ready. So it's e to the x. That grows exponentially, so faster and faster and faster. Now, the inverse would perform as the slowest function, which is the natural log of x. Okay? Everything in between, such as x squared, x cubed, x to the fourth, x to whatever power, right? So take a look here. Where is it getting larger faster? Press play when you're ready. It's getting larger faster. Neither. They're both traveling at the same speed, so you focus on their degree here. That -1 and that +1 has nothing to do with it because those are constants. If you guys think about it logically, when n gets really large, that -1 and that +1 has very little to do with the speed. So since they're traveling at the same speed, you look at the coefficients. Okay, so if you notice there, 1 divided by 1, that just comes out to 1. But more importantly, we're not just taking the limit, we're running the divergence test, right? So did the limit come out to 0? It did not come out to 0. So what does that mean? So remember, as long as the limit does not come out to 0, it will diverge. This limit did not come out to 0. Therefore, the series diverges by the nth term test. Okay, I'm just being flexible with the explanation. You can use the divergence test or the nth term test. And that's it. We're getting rid of all the bad series, all the series that diverge, that gives us no information. Okay? Let's do a couple more. Here's part C. Okay, try this one on your own and then press play when you're all done. Okay, here we're going to run the divergence test. We're going to take the limit of 1 over n as n goes to infinity. It's definitely getting larger in the denominator here. The numerator is just staying at a constant 1. So when the denominator gets larger, we know that this comes out to 0. Okay, what does that tell you? This comes out to 0 exactly. So you guys remember, if it doesn't come out to 0, right? If it doesn't come out to 0, we know it will diverge. But what if it does come out to 0? It does not mean the opposite, okay? If it comes out to 0, that means we don't have enough information. Don't say that it converges, okay? Therefore, the series is inconclusive. That just means we don't have enough information to make a statement that it will converge or diverge. Okay? The series is inconclusive by the nth term test. Okay? In fact, you'll learn later on that this actually does diverge. Okay? It's just that you guys don't have enough tools yet, but you will. All right, here's part D. Okay, try that one out. Press play when you're ready. Okay, here's the limit of n factorial all over 2n factorial plus 1 as n goes to infinity. We're going to run that divergence test. Okay, when n gets really large, okay, where does it get larger faster? So we notice that the numerator is traveling at a factorial speed, and the denominator is also traveling at a factorial speed. So you look at the coefficients. So the coefficients here are really just the 1 and that 2 right here. So the limit here comes out to 1/2. But more importantly, what does 1/2 tell you? 1/2 is definitely not 0. Therefore, the series diverges. How do we know that? By the nth term test. Okay? Get used to making a conclusion with a justification. You guys have been through a lot of FRQs to know that pretty much every conclusion you make has to be justified, especially when they ask you. And pretty much always they will ask you on the FRQ question for series, okay? Okay, so that's pretty much the divergence test. It's the first filter. We're getting rid of all the bad series, all the ones that diverge, okay? Okay, so here's the next one. Okay, this is the formal terminology here. This is called the geometric series test, or GEO series for short. Basically, and I'll go through this quickly because I'm going to refer to the worksheet. Basically, if you have a series that looks like that, where it's a times r to the n, based on what that r is, it will converge or diverge, okay? And then geometric series is one of the only series that will tell you exactly where it converges, okay? And I'll explain that in a second. Okay, so let's take a look at this real quick. For the geometric series, so you're on your packet over here, okay? So again, you're looking for a sub n r to the n. So you're looking for pretty much a sub n is just a number, some number in the front. But you're pretty much looking for r to the something power. So generally you'll see something like 4 times 3 to the n power, okay? Notice how that has a number in the front and some type of radius, and then to the n power, all right? More on the radius later. So basically, depending on what that r is, it will converge or diverge. So let's read this real quick. So they're ignoring the signs, okay? So sometimes your r is negative, sometimes your r is positive, but they're saying just look at the absolute value of it, okay? If your r happens to be less than 1, okay, or within -1 and 1, okay, it will converge, okay? Now, if the absolute value of your r comes out to larger than 1 or 1 exactly, you know it will diverge, okay? That's basically it. So the way I remember it, for instance, if you guys had 1/2 to the n power, okay, here's how I see it. If I graph that, don't write this on your worksheet, obviously. 1/2 to the n power looks a little bit like this, meaning that your area under the curve is getting smaller and smaller and smaller. That tells me that it will eventually converge, okay? Whereas if you had something like 2 to the n power, you would have something that just shoots straight up. And if you just analyze the area, it just gets larger and larger and larger. That tells me that it converges. That's not the formal explanation. That's just a little thing that I do in my head. So if it makes sense to you, go ahead and stick with it, okay? Again, that is in no way a formal explanation of it, okay? Okay, so again, the geometric series is the only series test, all right, that will actually tell you where it converges. Okay, so it's pretty much your first term over 1 minus whatever your r is. And I'll show you guys how to do that, all right? How do you know when to use this? Usually when you see n exponents, that's a telltale sign, okay? That is not the only way. There are some cases where it doesn't work, and this is why we're running through every test, okay? And again, this is the only test that actually tells you where it converges, all right? Okay, so let's test this out. Here's example 2. Part A. Go ahead and write that down. Just part A. All right, so first what we want to do is we want to run the divergence test. Okay, remember the divergence test is our first filter, all right? But here's what we're going to do. I'll write it out for you guys to see. But basically, we're going to take the limit as n goes to infinity. This is what I'm doing in my head. And you will get more and more comfortable with this, right? When n gets really large, we have 3 to the n over 2 to the n, right? Where is it getting larger faster? Well, 3 is an exponential function and 2 is an exponential function. 3 is definitely going to it'll grow a lot faster than 2. So we know the top is getting larger, so you know this here does not exist. Okay? More importantly, it's not 0. So we know it will diverge. Okay? And this is why you run the divergence test, because you get rid of all the bad ones first. But we know it'll diverge. But for the sake of running the geometric series test so that you guys are comfortable with it, let's run it this way, okay? So what we're going to do is first we want to make sure that it looks like something to the n power, in which it does. So this tells me that my r is 3 over 2. Actually, my absolute value of r is 3 over 2, okay? Which is definitely larger than 1. 3 divided by 2 is 1.5. It's definitely larger than 1. So if you guys look back at that sheet, okay, when r is larger than 1, it will diverge, okay? Therefore, the series diverges by geoseries test, okay? Meaning that this will go out to infinity, okay? Okay, so in this case, we were able to use 2 different tests, not always, 2 different tests to prove its divergence. Okay? Okay, let's do a couple more. Here's part B. All right. Now here, does it look like something times something to the n power? Does it look like something times something to the n power? And it kind of does, right? But not really. So we actually have to rewrite this here. If I bump this out, if I scoot it over, I'm going to have 3 times 2 to the n. Or something over 2 to the n, right? I could put an invisible 1 right there. This just involves you knowing how to rewrite it. 1 over 2 to the n is the same thing as 1/2 to the n power. Because if you think about it, if you take 1 to the n power, 1 to any power is just 1. So it's really the same thing. So again, you're just getting used to rewriting. So before we run any test, there we go. Okay. Now if you take a look here, if we ran our first test, the divergence test, if we take the limit as n goes to infinity here for 3 over 2 to the n, we would actually get 0 because it's getting larger in the denominator. And remember, that tells us nothing. It's inconclusive. So we're going to have to resort to another test. All right? Just letting you guys know what's going on through my head. Okay, so we have the perfect setup for the geometric series test. Okay, so we look at our r. What's our r value? It comes out to a positive 1/2. And is that greater than or less than 1? 1/2 is definitely less than 1. What does that tell us? If you guys go back to that worksheet, when the absolute value of r is less than 1, okay, we will know that the series converges by the geoseries test. Okay? So here's the thing. All right? Very important. So because it converges, the geoseries test is the only test that actually tells us where it converges. So we follow we follow their formula, right? It's the first term, that's just the first term, over 1 minus r, okay? Now the first term, if we take a look at this series here, n starts at 0. So if I plug in 0 into n here, I will get, sidebar, 3 times 1/2 to 0 power. 1/2 to 0 power is just 1 times 3 is 3. So I know my first term is 3. 1 minus my r, the r is a 1/2. Okay, notice how this doesn't have the absolute value, so watch out for that, okay? So 3 minus 1/2, if you guys crank this out real quick, you'll get 3 divided by 1/2, which comes out to 6. This tells us that this will converge to a value of 6. Exactly. All right? So if your series does converge using the geoseries test, then you could tell me where it converges to, okay? So I'll write converges to 6. All right? Let's do a couple more. Pretty much from what I've seen in the past few years is that you guys just need exposure, okay? You need to see enough problems to kind of get the hang of it. Go ahead and copy down part C and try it out on your own and make a conclusion, okay? Press play when you're ready. Okay, here I have the perfect format. I have something times some number to the nth power, okay? But remember, I want to run my divergence test, okay? If I take the limit of this, okay, 3 to the n over 4 to the n, 4 to the n moves faster, so I know my denominator will get larger faster, so I know that limit comes out to 0. So I know that divergence test tells me nothing. Okay, it's inconclusive, right? But I'm not going to write that out. You guys should always run the divergence test through your head, all right? Okay, so we take our r. The absolute value of r comes out to 3/4, which is definitely less than 1. And what does it mean when it's less than 1? We know that the series converges, okay, by the geoseries test. Since it converges, we're going to run that test here. If n is equal to 0, I'm going to be left with a 2. So that's our first term, 2 over 1 minus 3/4. That's 2 over 1/4, which gives me 8. I'm doing the fractional math very quickly. Feel free to pause and play if you need to. But this is where it converges to. Okay, hopefully you got that too. If you didn't, reach out to me, okay? Here's part D. Okay, try this one out. Press play when you're ready. So the absolute value of r is the absolute value of negative 1/2, which is 1/2, which is still definitely less than 1, okay? Side note, the divergence test, I ran it in my head. It doesn't work. It's inconclusive, okay? Okay, so because the absolute value of r is less than 1, I know the series will converge. The series converges by the geoseries test. Okay, and since it converges, I know I can find out where it converges to. So here, if you guys pay attention, n starts at a different number. All right? So what you guys got to do is you got to plug in the very first term, n equals 1. So I'll do this on the side here. 2 times negative 1/2 to the first power, okay, is just 2 times negative 1/2, okay, which gives me negative 1. That is my very first term, okay? Sometimes n starts at 0, sometimes n starts at 1, sometimes n starts at 2, okay? The only thing that changes there is what your first term is going to be, all right? But it will still converge no matter what. So your first term is negative 1. A lot of people will put 2 at the top. Be very mindful of that, okay? All over 1 minus, now r is negative 1/2, We don't plug in the absolute value of r, okay? We plug in r. So here, we get negative 1 over. That's 1 plus 1/2, which is just 3 over 2. And if I multiply by the reciprocal there, I'll get negative 2/3, which is basically where it will converge. Okay, so again, exposure is pretty much all you guys need, all right? That's pretty much it. If it converges, find out where it converges to. If it diverges, your job just got easier, okay? But again, big takeaway, don't forget to run your divergence test, at least in your head, okay? Here's the last test for the day. P-series. All right, so going back to your worksheet here, P-series is pretty much whenever you have 1 over n to the sum number. So here it's a little bit different because geometric series, n was your exponent. Whereas now n is your base. And that's how you guys remember it. I wrote it right over here. Obviously it looks like the partial sum indicated. Why did I write that? Okay, I'll come back to it. Well, anyways, you're looking for 1 over n to the something power. And that's how you know to run the P-series test. I'll tell you guys right now, all of these tests are very easy to run. The tough part is knowing which test to use. Okay, so keep that in the back of your mind, all right? So again, divergence test, we run it always, right? Divergence test, we run it always. And if you notice that there's something to the n power, you might want to use the geometric series test. But if you notice it's 1 over n to the something power, you're going to run the P-series test, okay? Same idea when the p-value, so when the exponent is larger than 1, it will converge. Less than or equal to 1, it will diverge. Okay? So again, I'll get to this one in a second. But here we go. Let's run it. Exactly what I said, okay? But more convenient in a chart, all right? Here's example 1. I'm sorry, 3. Part A. So we actually solved this problem earlier. If I can scroll back here. Right here. Right? We were trying to use a divergence test, and then we concluded that it was inconclusive because the limit actually came out to 0. That doesn't mean it diverges or converges necessarily. Okay? So what we do is we run that p-test, okay, the p-series test. So we notice that it's 1 over n to the something. Now, what is that something? That degree is 1. So we know that p is equal to the 1. Okay, what does it tell you when p equals 1? So let's go back to our chart here. All right, so when p is exactly 1, we know it's going to diverge, okay? Therefore, the series diverges by P-series test. Okay, now, this is a very common series, okay? You guys need to add this to your, what word am I looking for here? Not vocabulary, but I guess vocabulary. Okay, this is a very common series that's used, okay? We have a special name for it. It's called the harmonic series. Okay? It is common. It is a common understanding that a harmonic series diverges. Okay, so 2 things that you guys can do. You guys can say that the series diverges by the P-series test, but because this pops up so often, you could also say the series diverges because it's harmonic. That's it, okay? It is a common understanding that whenever you state that something is harmonic, we know it will diverge. Okay? Feel free to use both, but again, this pops up a lot, so I encourage you guys to use harmonic series, okay? And that's what I wrote in the notes there, the comments. Okay? Doesn't matter where it starts, okay? 1 over n will always diverge. Okay. Here we go, part B. Write it out. Okay. It's perfectly fitting. It's 1 over n to the something power. So P here is 2. Okay. Which is definitely greater than 1. So what does it mean when it's greater than 1? Let's go back to our chart here. Okay, when P is greater than 1, we know it will converge. That's it. The series converges. Okay, so here's the thing by P series test. This is not harmonic, all right, because 1 over n squared, okay? We know that it converges, right? But we don't know where it will converge to. Okay, the only time we can figure out where it converges to is if we have the geometric series. Okay, so it's cool that we know that it converges, but we don't necessarily know where it will converge to. All right. Okay, let's keep going. Here's part C. You can try this out on your own if you'd like. Press play when you're ready. Now this one here is just as easy. It looks a little bit complicated because it's not in the perfect setting, okay? Just like how you guys had this one right here. You had to do a little bit of work rewriting it in order to make it look like a geometric series, right? Now here, same thing. In my head, the divergence test, if I run it, I will get 0 because it gets larger in the denominator. So I know it's inconclusive. I can't use the geometric series test here because I don't have n as an exponent. Okay, so I know this has to be P series, but it doesn't look like 1 over, n to the something power, okay? So here's what you guys need to know. First off, that 3 is a coefficient. And just like with integrals, that coefficient can go on the outside. Okay, so that leaves me 1 over. Now, sidebar here, n, radical n, is the same thing as n times n to the 1/2. Square roots, right? And if we multiply with the same base, we add our exponents here. So that's n to the 1 plus 1/2. Go ahead and do that real quick. So that's really just n to the 3/2 power. Okay. So this is a perfect fit. We have 1 over n to the something power. So we know that P equals 3 over 2, which is definitely larger than 1. Okay, think about what that means when it's larger than 1. Okay, when P is larger than 1, boom, right there. Okay, we know it's going to converge. Therefore, the series converges by P series test. And that's it. All right. Okay, so last thing before I, you know what? Maybe I'll just stop here. You know what? Yeah, let's save that for later. So remember, you've learned 3 tests so far. You're pretty much trying to figure out where or which series will converge because series that diverges gives us no information. It's not as interesting, right? So remember, we always run the divergence test in our heads at least, okay? If it comes out to anything besides 0, we know it's going to diverge. More importantly, if it does come out to 0, you don't say that it converges. You just say that it's inconclusive, okay? Now, geometric series tests, you're looking for something to the n power in order to use the geometric series test. Now, if your base or your radius is less than 1, will converge. Anything larger than or equal to 1 will diverge. Geometric series test is the only test that actually tells you where it converges to. And if you have 1 over n to the something power, then you're going to run the p-series test. So if n is your base, most likely you're going to use the p-series test. If that exponent is greater than 1, it converges. Less than or equal to 1 diverges. Okay? So make sure that you guys master these 3. I've posted up the homework as well for you to practice these 3 tests here, okay? But if you have any questions, please do let me know. All right?